So from this lecture 12, we are going to discuss the CMOS inverter. Now we have NMOS and PMOS working together. And it has 3 lectures. So first one, we are going to discuss operation principle and the noise margin. So this is the Sakura Smith's book, chapter 13.2. And the lecture video from Professor Kang. Okay, so the CMOS inverter. And you may have seen this kind of symbol before in like 2020, I guess. So in the logic circuits, if you want to invert your digital signal from 1 to 0 or 0 to 1, you have this symbol, triangle with the circle. Circle means inversion. So this is inverter. But actually you need to implement this into the silicon using transistor technology. Right? This is your digital circuit, but that's just a symbol. That's not real. What is real on the chip is those 2 transistors, one NMOS, one PMOS. And then they have this kind of connection. So the NMOS source is ground. So this is the source of NMOS. NMOS gate and then PMOS gate are collected together as the input voltage Vin, or this Vi. And PMOS, as we discussed, higher potential, okay, is the source. So if connect to the power supply VDD, so then this is source. So then both drain of the NMOS and PMOS are connected together as the output voltage VO. So that's the connection of the NMOS and PMOS. So you know the truth table for the inverter. Just invert the signal from 1 to 0 and 0 to 1. That means digital level. But in the real circuit, you are looking at this kind of relationship between input voltage and output voltage. So the input voltage is 0, output voltage will be VDD, power supply. And the input voltage, VDD, output voltage is 0. So use VDD as the logic level 1 and the ground 0 as 0 logic. So any questions? Alright, so this is a building block for your digital circuit. Just invert the signal. And we are going to discuss in details how this inverter, CMOS inverter, works. Because this is CMOS, you have NMOS and PMOS. Alright, so this again, you see this kind of cross section. You have seen this in the previous lecture. And the NMOS is to the P-type substrate, and PMOS will be built in this N well. And you ask about the body contact. Where is that? Okay. So body contact is here. So the body contact with the P-type substrate, you can have a P plus doping region as a body contact. So this is body contact. And then you ground the N plus and P plus. This is source. You will ground both source and body of N-type together. Or in the circuit symbol, you can ground this S and B together to the ground. So similarly for the P-type, the body, because this is the body to here. So you will have a N plus doping for the P-type body, and then the P-type source and body are connected together. Both of them will connect to the VDD. So here in the symbol, you will have the B and the S connected together to the VDD for the PMOS. And then the input voltage applied simultaneously to the gate of NMOS and PMOS. and then the output voltage is coming from the drain of the PMOS and NMOS together. So that's a connection. Any questions? Alright, so this is a cross-sectional view. But actually, from the top view, this is a layout of the inverter. So if you are a circuit designer, you will always deal with this kind of layout eventually. So here in this class, we don't require to read this kind of layout. But if you take more advanced circuit design or VLSI design, like the, I think 4130 maybe, the advanced VLSI system, so you will deal with this kind of layout. So this is from the top view. You look from the top down to the silicon. You will see this kind of layout. And basically here different regions are for different, let's say, different source and drain region. So here the bottom one, this is NMOS, and this is a PMOS. So here, this is the input contact, and this red wire, this is interconnect. This is the interconnect we have talked about before. So this metal wire, this red one, is a gate of NMOS and PMOS. So here this is NMOS, and this is PMOS. And then this is like a top view of the transistor. So you have the gate here, and then that means you have source and drain like this, and your channel is along this direction. So the like this red region is the gate wire, and then the green region is like your doping region, and then this black square is like a contact wire from the bottom tier to upper tier to collect vertically. So then similarly for and this is let's say this is body contact. Similarly for the PMOS, you will have the drain here, source here, body here, and for NMOS, body and source will connect to the ground. Similarly for PMOS, body and source will connect to the power supply. And PMOS, the only difference here, the PMOS will have additional square. This gray box here, this is N-well. You need to first dope this area with N-type, because the substrate is P-type. You need to make that region N-type first. So I don't require this kind of layout in this class, but this is how the layout looks like for the CMOS inverter. And if you are a circuit designer working in, for example, Apple or Qualcomm or those design companies, your eventual product is this one, to generate the layout of the circuits. Basically, you need to define the geometry, or the geometry here, like the distance, the length, the dimensions. And then you're going to send this layout to the manufacturer. For example, the TSMC or Samsung foundry, they will fabricate the chip based on the design rule you set up here. So here the different color means different process. You need to first make, for example, the N-well. You need to dope that region with the N-type doping. And then you do the definition of the gate. The red one, you are going to deposit the gate MOS structure. You build that MOS structure there, and then you finish the doping. The green ones with like N+ type doping for source and drain for the MOS. And after that, you need to make the contact. That means you are going to make metal wires connecting to your source and drain through that black box. and then later you need to build the power supply and the ground metal wires as interconnect. So it's like step-by-step definition of the manufacturing process through the layout. So the layout defines that geometry information, basically. All right, so this is from the top view. You look from top to the silicon. So here, let's look at the so-called voltage transfer characteristic, or sometimes we call it voltage transfer curve, VTC. So basically, it's a voltage relationship between the output voltage VO versus the input voltage VI. So if you think about your inverter, input is VI, output is VO. So what is the voltage relationship between VI and VO? So it's something like this. Okay. If the input is, let's say, the x-axis is input is small voltage, let's say 0, then your output will be VDD. But as you sweep the input voltage from 0 to VDD, your output voltage will drop from VDD to 0. So this is like inverter. But here we will have some definitions. Okay. First, this VOL is the lowest output voltage or the output node, and in the CMOS inverter is 0. And then the VOH is the output high. So in CMOS is VDD because the dynamic range, let's say, is 0 to VDD. So this is the two possible output voltage, highest and lowest. And then the input voltage range, VIL, is the input voltage low, VIH is input voltage high. So this can have a larger range. So for the input, let's say here, this VIL is defined when the slope of this curve is -1. So that means 45 degrees pointing to the second quarter. So this is a -1. Then this defines the VIL. So basically, if your input is within this range, you can think your input is digital 0, because still the output you see here is close to the VDD in this range. Is in this range. So the output is high, even though your input has a range from this 0 to VIL. Or in other words, we can define this as the noise margin for the inverter. So that means even if your input is not ideal 0, if you have some noise in this range, your input voltage is in this range, the output can still be reasonably good as a high voltage. So this is the advantage for the CMOS inverter. It can reject some noise when you do the computation. Even though the input is not ideal logic 0, because ideally it should be close to 0, but even with some noise within this range, your output is fairly close to the logic high. Similarly, you can define the input voltage high range. So that is from this VIH to the VDD. So in this range, you can think this is a logic high input, because the output will be fairly low, close to 0. Or if you look at the voltage range here from 0 to VDD, so your input can have this kind of logic 0 range from 0 to this VIL. And input logic 1 can be this VDD down to the VIH. And after the inversion, after this inverter, then this one will become fairly close to the, if this is the input, this is output. And this one will become fairly close to 0. So that means the noise is reduced after this inverter. So that means here you add some noise to the input after this inverter, then the noise is reduced. And then you can also inject another noise here, then after the inverter, the noise will be reduced. So you can buffer these multiple inverters. So your noise will not propagate in the digital circuit, because each stage we are going to reduce the noise. Any questions? So this VTC is important. It characterizes the noise margin. So basically here we can understand why this is flat initially. So why is that? That means the input voltage is low. Okay. So this input voltage starts from 0 until you reach the VTN. That is the threshold voltage of this NMOS here. Before you reach that, this NMOS is off. That means current is very small. Current very small. That means almost no current flow. No current flow, then this output voltage will be the same as the VDD. Because if you have current flow, then you are going to build some IR drop, voltage drop across this PMOS. But now since the voltage is very small, the current is very small, so this voltage drop is also negligible. So that means the output will be the same as the VDD. Because this is off, it's like open circuit. Then this voltage is the same as this one. Until you reach this threshold, then this transistor NMOS is turned on. After NMOS turned on, that means you have some current flow. If you have current flow, because those two transistors share the same branch, so that means this drain current NMOS and PMOS will be the same. So if you have current flow from the PMOS, then this current will build up some voltage drop across the PMOS. Then your output voltage will start decreasing. As you further increase the input voltage, this current will become larger and larger. And then this voltage drop along the PMOS will become larger and larger. So eventually then you will start dropping the voltage. And until some point, if this is high enough, this input voltage is high enough, then PMOS will be turned off. After PMOS is turned off, then no current flow. That means this NMOS is completely on, and then this output voltage will be the same as the ground eventually. So you will have this process when you sweep the voltage from 0, input voltage from 0 to VDD. Then you go through a few stages. Like first the NMOS change from the off to on, and later PMOS change from on to off. So let's look at this ideal CMOS inverter. So ideal case here, we assume the transistor has the square law current in the saturation. So we only consider the first order effect, basically. That means ideal. we don't have the channel length modulation, those second order effects, or this drain lowering, drain induced barrier lowering. So it only considers the simplest standard IV equation. So if you only consider that, then the curve will become something like this. This will be sharp and will be vertical. And then if we use that, then we can derive some of the voltage in this curve, like the VIL, which we define the slope become -1 here. If we use a simple square law equations, then we can derive what is this VIL. And here we also assume the matched case. Okay, so this is an important concept. So what is matched case? So the matched case, the matched CMOS, that means NMOS and PMOS are matched. Matched means, by definition, okay, this transition point is in the middle. So here, typically we'll also draw a line, 45 degree. Because this line means VO equals to VI. And then the intersection here with the VTC curve will determine so-called V middle, Vm point. And this Vm point, if it's half VDD, power supply VDD, if it's exactly half, then we'll call this is a matched case. So the NMOS and PMOS have the same kind of symmetry. So to make this matched condition, we need to satisfy the following. First of all, the NMOS and PMOS should have the same threshold voltage. This is the first condition. Because that threshold voltage will determine where the decay of this happens. So you want to be symmetric. So then NMOS and PMOS should have the same threshold voltage. And secondly, you need to satisfy this condition. You want at this Vm point, the NMOS and PMOS currents are the same. Or let's say the conductance of the NMOS and PMOS are the same. So you know at this point, both NMOS and PMOS transistor will be in the saturation. So the current, you know, NMOS, and then you have some voltage term. It's VGS minus VT. That will be the same. Because here it will become, the VDS will become the same. VDS is half VDD for both. And VGS is also the same. Because VGS will be half VDD. So it will be half VDD minus VT. And here will be half VDD minus VTN and VTP. Of course, here we take absolute value for the PMOS. So you want this to be the same. So in front of the voltage term, you want those to be the same. So this Km per W over LP needs to be the same as Kp per W over LP. And you know Km per and Kp per is essentially mu n COX and mu p COX. COX is the same for the same technology node. COX is the same. Then eventually you will get this one. The W and also L is the same for the same technology node. So what is different is the W of the NMOS and PMOS. The width of the transistor is different. And the PMOS is to be wider than the NMOS. Why is that? Because we just showed for example, if mu n is like twice mu p, then WP is to be like twice mu n to satisfy this condition. So this is generally true for the CMOS circuit design. If you want to achieve this so-called matched condition, as a circuit designer, you have to size your PMOS wider than the NMOS. That goes back to the layout we have shown here. So you have to make this region is wider than the NMOS. So this is true here even in this layout, because WP is here, WN is this one. You see this WP is wider than the WN, the width of the transistor. So your job as a circuit designer is to determine those W. Because as a circuit designer, you cannot change the L. The same topology load, you have the same L. And you go through the same fabrication, so the oxide thickness is also the same for the NMOS and PMOS. So the only thing that is different you can make is the W of the NMOS and PMOS. And you need to adjust that based on the mobility ratio in this technology node. Of course, different technology node is different, like 65 nanometer versus today's 10 nanometer, 7 nanometer, then that ratio may be a little bit different. So you need to fine tune this. So why do you want to have this matched case? What do you care about this matched case? Any idea? Because you want everything to be symmetric, right? So for example, your noise margin for the low level and noise margin for the high level, you want them to have the same noise margin against the noise to the low level or the noise to the high level. And later you will see that in this matched case, the NMOS and PMOS switching speed will be the same. So that means your transition from 0 to 1, 1 to 0 will be the same. So this is what we are going to discuss in the later lectures about the delay or the switching speed or the clock frequency of your circuits. So all of those depends on this matched condition. Alright, so I think that's the end of today's lecture.